Okay, so if we have an elastic force, then it's governed by Hooke's law. So that if we stretch a spring by a meter, and that requires a force F, to stretch it twice as far is going to require twice the force, because the force varies directly with extension. This, of course, is Hooke's law. And Hooke's law says that the amount of force is directly proportional to the extension, and the coefficient of proportionality is the elastic constant K in units of newtons per meter. And if we plot a graph of the force versus extension, we get a nice straight line, and the slope of that graph is the spring constant K. So that's the familiar Hooke's law. Now the problem that we're interested in is going to be the work done in stretching a spring. Oh, I suppose, okay, elastic constants. Something that's really stretchy has a small elastic constant. Something that's really stiff has a really big elastic constant. And then something in between, well, it has got an in-between elastic constant. So K is sort of proportional to the stiffness of the material. It also depends on the size of the material, too, as we'll see in future courses. So if K tells us a ratio of the number of newtons per meter, so if we stretch 1 meter at 10 newton per meter spring, it requires 10 newtons of force to do so. So well, let's draw a nice straight line. That's a good idea. Okay, let's try it and see. Oh, that's nice. Look at that. Okay, good. So now, 10 newtons per meter. So 10 newtons to do 1 meter of extension. So, and we want to find the amount of work done in pulling on that spring. Well, we know that a work is a force times a distance, right? Now, clearly the distance is a meter, but the question is, what do we put in for the force? Because it doesn't make sense to say 10 newtons, because it was only 10 newtons when we reached the very end of the extension. Likewise, it doesn't make any sense to say 0 newtons, because it was only 0 newtons at the very beginning. But what does make sense is to average those two, because on average, we were exerting 5 newtons, and we've done 5 newton meters or 5 joules of work. Now, what this is really doing, of course, and if you take Cal 2, you'll know this, an average force is related to the area under the graph. So the area under a force distance graph, we see here that we really have a triangular shape, and the area of a triangle is a half times the height times the base. So this is 10 newtons of height, half of 10 newtons times 2 meters, and so we get the same answer of 5 joules. So thus our fifth equation, which says that work is either the area under a force distance graph or the average force times the displacement. Now this is an example that we won't get into, but it's quite an interesting one. We'll do it in the next course in biological physics. The elastic constant depends on the material, the cross-sectional area of the thing we're stretching, the spring or the tendon or whatever, and then the length. So this just draws out material, what really depends on the material, and then these are obviously the dimensions of the elastic thing, the spring. More on that in a future course.